Greetings. Today we're going to learn about principle of inclusion-exclusion. Sometimes people like to abbreviate this PIE, P-I-E, principle of inclusion and exclusion. Now, this principle in its full form and notation-wise, it's a little gnarly. Let's ignore that for now, and let me give you some examples first, and then we'll come back and look at that notation. So let's think about two sets. Suppose I have a set A and a set B, and I'm interested in looking at the size of their union. We can sum up the sizes. So then one set is here, the other set is there. But of course, as we are summing up the size of those two sets, we double counted the intersection right there. So we should compensate and subtract the size of their intersection. So that is how we could count the size of that union. So you know that. Now let's consider the case where we have three sets instead. Say A, B, C. And again, we're interested in looking at the size of the union of the three sets. So again, let's add up the sizes of the individual sets. This time I won't shade. I hope that you can imagine that I'm shading it, and you'll notice that when we sum that up, then we do get this region, and this region, so that's good. But we would have double counted this region, and that region. So we want to subtract the intersections. So let's subtract the size of the intersection of A and B, so then we get rid of that starred region, and then also subtract the intersection of A and C, and also the size of the intersection of B and C. So we subtract out those three stars. But as we're doing that, what about that triple intersection in the middle right there? Let's think just for that region, how many times we counted it. We counted it once in here, A, B, and C, so we counted it 3 times in that intersection. And then when we subtracted it, here, A intersect B, we subtracted it once, second times, a third time. So we subtracted out the middle 3 times. So in fact, this is what we've counted so far. We've added in all the things that are only in one set, and then things that are only in 2 sets, we added it twice and subtracted once, so now we counted it once. But how about that thing in the middle right there? We haven't counted that. So now we must add in A intersect B intersect C. And that's inclusion, exclusion right there for you. Okay. So we include and then exclude and then include. And that pattern is quite marvelous. It works out very, very well. So let's look back at here. So let's look at this one. If you have n sets and you're looking for the size of the union, you add in all of the single set sizes. You subtract all the double set sizes. There's n choose 2 of these. And then you add in all the triple intersections, you subtract all the quadruple intersections, and keep going until you get all n of them to intersect together. The plus or minus is because it depends on the parity of n. If it's even or odd, the alternating signs might end with a negative or a plus or a minus or a plus at the very end. Now, it's quite marvelous that the pattern works out so simply. Who knew? Like, were you a little bit surprised when we got here and we only need to add in 1 copy of the intersection? Maybe after doing these 2 steps, the number of intersections in the middle, maybe we need to add 7 copies or maybe 2 copies or subtract a copy or something. But it alternates like that, and it's quite marvelous. So that makes this formula simpler. And then if you come back to the way that it was written here. So that's a union, just like a summation notation. That's a big union of n sets, I going from 1 to n. So that is exactly this notation right here. And then we look at the size of that union, and that's equal to the sum. And look here, we have an index set I, and you look at the intersection of all the sets. So for instance, I might be 3, 7, 8. So then you look at a sub 3, a sub 7, and a sub 8, and then you intersect them together. So that's one of the terms down here. And then you need to know whether to add or subtract. And the standard way to get alternating signs is raise -1 to some power. So if you have 3 things in your index set, like 1, 2, and 3, then the size of the index set I would be 3, plus 1 would be 4. That's even number, so -1 to even number would be a plus sign right here. On the other hand, if your index set is consists of 2 things, say n-1 and n, then you'll have 2 things in your index set, and then so the size of the index set is 2, plus 1 would be 3. That would be odd number, and so you have a negative sign. In any case, this -1 raised to the index set size plus 1 gives you this alternating behavior of plus when there's a single thing in your intersection, minus when there are 2 things in your intersection, and then alternating even, odd, depending on that. And finally, the index set ranges over X. What is X? X consists of all non-empty subsets of your indices, 1 through n. It says non-empty because you don't want to have an empty set and then try to do it over here. So you take all the non-empty subsets, just like down here, I took 1 set, and 2 sets. I didn't take 0 sets and try to write something over there. Yeah, so 1 set or 2 sets. And then down here, 1 set, 2 sets, 3 sets. I didn't try to do 4 sets because I don't have 4 sets, but I also didn't write a line for 0 sets. So that's where the non-empty things comes in. Now let's try this principle of inclusion and exclusion on a concrete example. Suppose we have a standard 52 card deck, and we want to count how many cards are in these categories. Usually in class, I would pause and let you try this. You should probably pause this video and try it right now, but otherwise I'm going to talk through part A, B, and C right now. D is usually a filler for people who work faster to have something to do in class. So let's talk through part A. Again, pause and try this yourself. So I'm looking at heart or face cards. So let me say that H is a set of hearts, and then F is a set of face cards. And we're looking for hearts or face cards. That means H union F. If you think about the Venn diagram, H you would want to count, F you want to count, and their intersection you don't want to count them twice. So by inclusion, exclusion, you add in all the hearts, add in all the face cards, and then you want to subtract out the hearts and face cards that you counted twice. So how many hearts are there? There are 13 heart cards in a standard deck. And then for face cards, there's 12 face cards in a standard deck. 4 suits, each suit there are 3 cards. So you can count that way. Yeah. So 12 is from 4 times 3. And then finally, we need to subtract H intersect F. So that would be set of hearts and face cards, so that are heart face cards. So those are 3, the Jack of Hearts, the Queen of Hearts, and the King of Hearts. So I hope that with this concrete example you see why we're subtracting 3, because here we counted all hearts, here we counted all face cards, and the cards that are the 3 cards I named got counted once here when I was counting hearts, and also counted here once when I was counting face cards. Now part B asks, what about hearts or face cards or black cards? So then let's continue with this example. So part B, let's say B would be a set of black cards. Half of the deck would be red cards and half of the deck are black cards. And we are looking for heart or face card or black. By the principle of inclusion and exclusion, we want to add in all the sizes of the individual sets, and then we want to subtract the intersections, the pairwise intersections, and then we want to add in triple intersection, all triple intersections. If there are more sets, then we'll have many triple intersections, and then subtract all the quadruple intersections and so forth. But this is where we stop. So here's the same numbers, 13 plus 12 hearts and face cards. The number of black cards, half of the deck is black, so we have 26 cards. And then we'll subtract these three intersections. The first one we already had from before. How about hearts and black card? Notice the intersection turns into an and. Yeah, it looks like and if you're thinking about the criteria. So heart and black, well, that's 0. Not possible. How about face card and black? Oh, that would be 6. There are 2 suits that are black, and then it's 3 face cards in each. Finally, hearts and face card and black. Well, that's not possible because heart and black, those 2 sets are disjoint. Yeah, just like here, that's 0. So this is also 0. So we see the minus 0 here and the plus 0 here. That's trying to account for this part. Now let's consider how that differs from hearts or face cards or red. Right? So these two look similar. Yeah, hearts or face card or black, hearts or face card or red. But because hearts are red, the calculations will turn out differently. So let's say R would be set of red cards. So we can try this again, heart or face card or red. And then maybe we can directly do this. So nothing changes here because it's still heart, face card, or red. Red and black are equinumerous, so they're both 26. Okay? And then minus 3 is the same because heart or face card doesn't change. Yeah. Now, how about the next one? It will be heart. Sorry, that wasn't heart or face card. Heart and face card. Now, then it will be heart and black. Now we turn into heart and red. Last time it was 0, but now we have minus 13. This is where it changes. Because here was heart and black. Here's heart and red. And then the next number is face card and black. Now we need face card and red. That doesn't change. And then finally, heart and face card and black turns into heart and face card and red. So what are heart, face card, and red? Well, you don't really need to say and red, right? Heart is already red. So just heart and face card. And we calculated that before. That's the minus 3 right there. So we have a plus 3. So you see these two give us different numbers. The minus 0 plus 0. Here's minus 13 plus 3. So just because the question looks similar, hearts or face card or black, hearts or face card or red, the calculations might be different depending on how the sets intersect with one another. If you zoom out for a moment, why are we using inclusion-exclusion to count these? It's because many times the intersections are easy to count. If you think about heart and face card, you can restrict your mind to just hearts and then think about which ones are face cards. But if you're looking at or, so unions, heart or face card or black, you cannot restrict your mind to just hearts and then add in face cards. How do you do that? Well, that's exactly what you would be doing here. You add in face cards, but you realize you added in too many, and then so you have to compensate. So in general, there are a bunch of situations where the unions are hard for you to directly count, but the intersections are easy for you to count because you restrict your mind to some set and then look further in how many of them are some of the other type and so forth. And that's why philosophically why inclusion exclusion works is because even though this side looks complicated, each one is easy to calculate. And then once you calculate each one together and you put them all together, then you get the other side. And often there's no easier way to count the left side, the union, without doing all the intersection work. So finally, the last problem is your homework. So I'm not gonna record a video on that. So that's it for today. Bye.